All right, welcome to Math 409, lecture 32. We're going to be doing one of the Putnam problems. It was either A1 or B1 from some year. Okay, so we have f of n is 1 factorial plus 2 factorial all the way up to n factorial. Find polynomials p and q such that fn plus 2 is equal to pn fn plus 1 plus qn fn.
Okay, so the
You can take off your mask because you're the teacher.
oh, okay, cool. So the first thing, well, what I'm gonna do is I'm gonna write up a solution that seems pretty straightforward, but it took a lot of computation to figure out the correct relation and then figure out like the nice kind of trick. You know, that's something Professor Miller has been telling us, like these A1 and B1 problems, like there's that easy like aha moment where it all kind of falls into place. So first thing, we're gonna write out this fn plus 2 term, which will be like so. So what we're gonna do for the next step, we're gonna split it up right here. Oops. So what we're gonna do is we're gonna factor out an n factorial from the first 3 terms here. And then the rest, we're gonna just use this fn notation. So we have fn minus 1 for this here.
What made you think to do this? Because you're pulling out a fn, you're isolating an fn minus 1, not an fn plus 1.
Right. Basically, we're going to get back an n factorial in a few steps, so that this will turn back into fn f of n.
Okay.
Yeah. And again, like this took a lot of computation to figure out like these steps, I guess. So let's see. Next step I have here is so I think what this step is moving toward is we're trying to reconfigure this to get an n plus 1 factorial instead of the n plus 2 factorial. So as we go forward, we get to here. And so we redistribute the n factorial into here, and then we're going to get it back here. So then it becomes n plus 3 times n plus 1 factorial plus n factorial. I guess this is when we can just go fn here. And now here comes the trick here, which is multiplying the old multiply by 1 trick is right here. So
Multiply by 1 on that 0.
yes, I think it's
Okay.
it'll be it'll be multiplied by 1. So the multiply by 1 will be so if you notice that this term is 1, And so let's see if I can fit it all at the end here. And so what's going to happen here is if we expand out, wait a second, sorry.
You'll have n plus 3 times fn plus 1 in the first two terms. Because if you factor out the n plus 3, you get n plus 1 factorial plus fn. So
Right.
this is going to be fn plus 1.
Right. Oh,
The
okay.
first two terms give you n plus 3 times fn plus 1.
Oh, yes, yes. So I see what's happening. Yeah. So we're factoring out the n plus 3 here. Kind of running out of space here. And yeah, so it turns out that this term is fn plus 1. So the final term here is n plus 3 fn plus 1. And so here, if we go back to the problem here, we have Pn is going to be n plus 3, and Qn is going to be minus 2 minus n.
Very nice. So you were divinely inspired.
Yes, yes. Yeah, basically, how I figured out the relation is I had to compute f of n up until probably n equals 6, until it became evident that this was the relation compared to something else that might have worked for the first three values of n. And like without a calculator, like it was, in the hundreds of thousands or millions computationally. So you had to add and subtract quite a bit and stuff. And then it took a little time to figure out kind of this algebra, kind of this trick here. So cool.
So I'm going to use this as a springboard to some fun math.
Okay.
So this is a nice proof. What I'm going to do now is I'm going to interpret what Jack has just done for us. And so I have not looked at this problem, but seeing how you've done it, I think I see a way to redo the algebra a little bit. And so what we can do is, so here's the problem. And so I'll cheat, I'll make it a little bit smaller to give myself a little bit more room. And so what you have is you have your fn is n factorial plus n minus 1 factorial plus dot 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 plus 1 factorial. Here's a nice observation. N plus 1 factorial is fn plus 1 minus fn. So we're only trying to find a combination in terms of n and n plus, in terms of fn plus 1 and fn. I can write n by n plus 1 factorial just as the difference of fn plus 1 and fn. Right? So if instead of giving you fn plus 2, if I asked you to do, okay, so now I want to do fn plus 2 in terms of fn plus 1 and whatnot. So if I replace, what's a good choice of n to take? Take n equals what? So does everyone agree with this identity? N plus 1 factorial is Fn plus 1 minus Fn. What's a good choice for n right now? Not 1. N plus 1. So if I take n equals n plus 1, and again, I'll put this in quotes so that people who are looking at this do not feel like at Williams College we don't understand basic algebra. That yields n plus 2 factorial is Fn plus 2 minus Fn plus 1. So the question is this useful for us? Well, it gives us a nice expression for Fn plus 2 almost in terms of what we want. So we now have Fn plus 2 is n plus 2 factorial plus Fn plus 1. So that's almost what we want. We're allowed to have a polynomial times Fn plus 1. We have that. But the other thing has to be a polynomial times Fn. Well, I've got an n plus 2 factorial. I already know how to write n plus 1 factorial as a polynomial in Fn plus 1 and Fn. So I can write this as n plus 2 times n plus 1 factorial plus Fn plus 1. And now I know that I can write n plus 1 factorial as Fn plus 1 minus Fn plus Fn plus 1. And now from this point, it's now going to be n plus 2 times Fn plus 1. Now I've got a minus n plus 2 and a plus 1. Oh, I'm sorry. This n plus 1 should come in here and make this an n plus 3, I think. Yeah. So it should be an n plus 3. I think I can. Yeah, I'll splurge and I'll use the eraser. And I get minus n plus 2 Fn. And so this is another way to do the algebra to get there. And again, it's trying to think which quantities do we know. And the key idea is once I have a nice identity like this, we saw this when we had that star operator, where we had this star operator, when you wanted something like A star, B star A is A, prove something with B star, right? It's once we have this identity, what's good things to substitute in? Well, I can write n plus 1 easily in terms of Fn plus 1 and Fn. And then if I have n plus 2 factorial, I can write that as a polynomial times n plus 1 factorial. I know how to deal with n plus 1 factorial, and I can just go down like that. The other thing to note is going back into the algebra that you were doing, you could have actually had the line in front of n factorial. You could have kept all of this here as Fn, because that's something that you need. This one was just along for the ride, right? And then you had that n factorial, and then you combined it back over here. So you actually could have put the line at n factorial, not at n minus 1 factorial. It's not wrong how you did it. So I want to use this now as a springboard to talk about something that Jack mentioned without forcing us to do it. So you said you actually did a lot of data collection to try to get a sense of what the polynomials are. That is exactly how you should do a problem like this if you don't see the solution. And the hope is that if you can do a small number of observations, you can get the answer without too much time. So we have for this problem, Fn is n factorial plus dot 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 plus 2 factorial plus 1 factorial. So we should make a little table, n Fn. So 1, 1. When n is 2, we get 3. When it's 3, we add 6, we get 9. When it's 4, we add 24 and get 33. 33. When it's 5, we add 120. So we get 153. When it's 6, we add 720. So 7, 8, 73. And when we have 7, we have something that's logical. Okay. The claim is the following. I seem to have lost the copy. So here is the problem again. So we claim that there's some polynomials P of n and Q of n that work. Okay, so we need to find if the world were really simple, what would be P of n and Q of n? Simplest case. One or more generally, constants. So we could try P of n, Q of n, degree 0 polynomials. It's not going to be that hard to figure this out. All right, so I would want, in this case, Fn plus 2 would have to be, say, P0 Fn plus 1 plus Q0 Fn. How many choices of n will I need to figure out what P0 and Q0 could be? I need 2, right? So take n equals 1 and 2, find P0, Q0 that work, and see that it fails for, say, n equals 3. I'm assuming that if you then tried to do n equals 3, it would not work. What's the next simplest thing you could try? I'm sorry? Linear. So could try, was P the first one? Could try, P1x plus P, I'm sorry, I guess P1n plus P0 and Q1n plus Q0. How many values will we need? So we need 4 values, right? Need 4 values of n to find P0, P1, Q0, Q1. Okay, 4 values of n, that's not too bad. And then we still have a couple of values to then check and see if it works. So this would actually allow us to find polynomials of degree 1 that work. Do you think we'll be able to find polynomials of degree 1 that work? Yeah, why should we be able to? Yeah, that's the answer, right? Well, you actually proved to us, and you hear the polynomials. P0, I'm sorry, P is n plus 3, and Q is negative n plus 2. So the coefficients aren't too bad. We have polynomials that work. The question is then, can you prove this by induction? So, again, I love the paste. So let's say we know that we conjecture P of n is, we said it was n plus 3, right? And Q of n was negative n minus 2. Can we prove by induction? So assume true for all n less than equal to k, or maybe we'll do k less than equal to n. All k less than equal to n, do k plus 1. The base case was done, of course, when we found the polynomials. So now let's see if we can prove this. So we would have Fn plus 2 is equal to n plus 3 Fn plus 1 plus, oh, sorry, minus n plus 2 Fn by inductive assumption. And now the question is, we need to show, does Fn plus 3, does that equal n plus 4 Fn plus 2 minus n plus 3 Fn plus 1? Right? Yes? All right, so let's paste this here. And so for the left-hand side, it's Fn plus 3 is n plus 3 factorial plus Fn plus 2, which is equal to n plus 3 factorial plus n plus 2 Fn plus 1 minus n plus 2 Fn. Is that right?
I think n plus 3. Fn plus
1. Oh, Fn plus 3, yes. And this is the inductive assumption. Right? So that's the left-hand side. So the right-hand side, I can write this as n plus 4. Let's do it slow, I guess. So we have n plus 4 Fn plus 2 minus n plus 3 Fn plus 1. We want to get an n plus 3 factorial. There's a lot of different ways to do this. So the question is now, what's the best way to do the algebra? Any thoughts? So we want to get things done in terms of just Fn plus 2 and Fn plus 1. We do know by assumption what Fn plus 2 is, right? We can replace this, right? So this would be the same as n plus 4, and then Fn plus 2 would be, is it n plus 3 Fn plus 1 minus n plus 2 Fn minus n plus 3 Fn plus 1, and this is the inductive assumption. All right, well, now we have an Fn plus 1, we have an n plus 4, n plus 3 minus an n plus 3, so that's going to just be an n plus 4 minus 1 times Fn plus 1. When I take the Fn plus 1s, I get n plus 4, n plus 3 minus n plus 3, so that's just n plus 4 minus 1 is just n plus 3, so I think it's an n plus 3 squared. Minus n plus 2 Fn.
I think you'd have to distribute out the n plus 4 of that to n plus 2 times n plus 4.
Oh, and this should be, oh, yes, thank you. And this should be an n plus 4 here, right? Fn. And so now the question is, can we see that this so this is something similar to what I just had, I think, in operations research. So again, a lot of this comes down to the algebra. It's fine to see bad ways to do problems. This idea was if we have a formula, can we just roll up our sleeves and do it by induction? This does not seem pleasant, but no, it's only been 10 minutes. We can actually even go back and check once I post this video how long this has been. You've got 3 hours. If it takes you 2 hours to do one problem and you get it right, that is a success. Getting one problem right on the Putnam is tremendous. Does anybody know anything about n+3 versus n+2, n+4? They differ by 1. This is the same as n+3 minus 1. This is n+3 plus 1. This is n+3 squared minus 1. So we could write this as n+3 squared fn plus 1 minus n+3 squared minus 1 times fn. Why is this useful? Well, if I look at n+3 squared fn plus 1 minus n+3 squared fn, what can you say?
I think you could reduce it down to n+3 quantity squared times n+1. As the other terms will cancel out.
Times n+1 factorial. So when I combine these terms over here, I'm going to get n+3 squared fn plus 1 minus fn plus fn. Well, fn plus 1 minus fn, this is a telescoping sum. Oh, no, sorry, not telescoping. This is n plus 1 factorial plus n factorial plus dot dot. This is n factorial plus dot dot. The only thing that survives is n plus 1 factorial, right? So this will be n+3, n plus 1 factorial, I think, plus fn. Oh, and this is squared. So notice we're trying to show the right-hand side is the sum of n+3 factorial all the way down, right? We're trying to show the right-hand side equals the left-hand side. What's fn plus 3? That's n plus 3 factorial all the way down to 1 factorial. We've got the n factorial all the way down to 1 factorial. We've got an n plus 1 factorial. We have here n plus 3 squared. So what I want to do is I want to have an n plus 3 factorial. That should be an n plus 3 times n plus 2. So I'm going to write this as n plus 3 times n plus 2 plus 1 times n plus 1 factorial plus fn. Because I'm trying to get this to be the sum of 1 factorial plus 2 factorial all the way up to n plus 3 factorial. I've got an n plus 1 factorial. I want to multiply this by n plus 2, n plus 3. So the first term is going to give me a n plus 3 factorial plus n plus 3 times n plus 1 factorial plus oh, sorry. Right, n plus 3 times n plus 1 factorial plus fn. Does everyone see how I get to this? How should I write n plus 3? N plus 2 plus 1. And now what will I get? I'll get n plus 3 factorial plus n plus 2 times n plus 1 factorial is n factorial plus 1 plus n plus 1 factorial plus fn. And that's what we wanted. So it is possible to prove this by induction if you know what to prove. So again, we had to be a little bit clever in the algebra. We looked at what the left-hand side was. We looked at what the right-hand side was. And the question was, can I just show that the right-hand side is equal to the sum from 1 factorial all the way up to n plus 3 factorial? And with a little bit of algebra, and the trick was, I want to write things out in a good way. I have an n plus 3 squared. I should write that as n plus 3 times n plus 2. And just keep playing games like this. So much of this is about trying to find the right way to look at things. We actually saw something very similar today in operations research. We were doing Simpson's method and we had some integrals to do. And it was better to add 0 in such a way to get things. So again, the whole idea is to try to give you a sense of how should you look at problems like this to do the algebra in a way that will work out. And because we can gather the data without too much trouble, we actually can figure out what these polynomials are. It will take a little bit of time. You'll have a 4x4 system of equations to solve. Is anybody doing cartwheels, jumping for joy at a 4? No, but it's not horrible. I'm not doing that. I am happy to use the divine inspiration that here's what they are in the interest of time in the class. But with 3 hours, I can solve a 4x4 set of equations. That's not a problem, especially when the solutions are nice. What if the polynomials happen to be quadratic? How many would we need? So if they were each of degree 3, you have 3 unknowns. So degree 2 polynomials, 3 unknowns. How many equations would I need? 6. And if I wanted to check, I would need a 7th point. I'd screw the checking or go through and figure out. What if they were quartic? Then you start getting really large ones. And then the question is, do you think that you will be able to solve if it's quartic, this is going to be an 8x8 with large numbers without making an algebra mistake. At that point, I'm no longer confident. But taking a gamble that they're polynomials of degree 0 or 1, it's not so bad. And you can do it by brute force. And then, just going through this, it's just, trying to find what is a good way to rewrite things. And so you said that when you were doing it by hand, you had some idea of how to attack?
Well, in coming up with this, I tried to, the first thing that occurred to me was, oh, maybe I can do it by induction, but I wasn't figuring it out. And somehow I came up with this.
Right. And again, I mean, the real inspiration was over here, writing it as n plus 3 plus -2 minus n. That's where the miracle occurred, that idea to write it like that. If you were doing this on a Putnam, is it fine to just write that without justification? Just say, I would say, note that n plus 3 plus -2 minus n equals 1, so we may multiply by 1. It's perfectly fine to do that. You don't have to say where the divine inspiration came from as long as the step is justified. Make sure when you're writing things on the Putnam that you explain why you're doing what you're doing, why it's justified. You don't have to say where the inspiration came. You just have to show that there is a justification for what you're doing. And here, this is perfectly fine. Looking at this, it's a little bit of a leap of faith. So I have some idea of where that came from. You've got an n plus 3 over here. By putting an n plus 3, we can kind of combine things. And an n factorial plus an fn is going to give us an fn plus 1. So it's a very reasonable thing to try to put in an n plus 3 factor over here. So you were doing things multiplicatively. I'm doing things additively. I'm basically rewriting expressions in such a way. So this is a really nice problem. There's multiple ways to solve this. If you can see the algebraic ways, that's the fastest. And again, very similar to that, convolution operator we had before. It's, can we come up with a good identity and then put in different values? So sometimes rather than putting in n+1, it might actually be better to do, star as, m+1 factorial is fm+1 minus fm, and then choose good m's. Use a different variable so that it doesn't confuse you as much. And then later, let's take m equals n. Let's take m equals n+1 and combine them and use stuff like that. When you have expressions, see how you can relate them. n+1 factorial is fn+1 minus fn. So maybe doing stuff like that is going to help me. Okay. Any other questions on this problem? All right. We only have, on the order of, 5 or 6 minutes left. So what I will do for the last few minutes is just, expanding on this. We have not lectured on the Pythagorean theorem in this class, correct? So the only choices you have in the Pythagorean theorem is which side do you want to make A, which side do you want to make B, and which way do you want to draw the triangle. Nobody ever draws the triangle going down. That's just wrong. But you can decide, do you want the vertical side on the far left or the far right? All right. And so the Pythagorean theorem is a squared plus b squared equals c squared. And so the question is, can we prove this? Yes, many different proofs. And if we can't prove it, can we at least see that this is reasonable? So the simplest guess. So can you tell me how the Pythagorean theorem must be as a function of a and b? What kind of function must it be of a and b? So imagine we're trying to guess the relationship between a, b, and c. And I tell you, there's some relationship between a, b, and c. What should be true about the relationship involving a and b? Well, okay, so they're the two sides. So I claim that there's some function a, f of a, b that equals c. What must be true about the dependence of the function on a and b? What if I switched a and b? What if I did f of ba? Should that be the same? So the first thing we know is it should be symmetric. So let's guess linear Pythagoras. So maybe alpha a plus beta b equals c. If we look at extreme triangles, if we look at a triangle that's very long and thin, in the limit, what's going to be true about a and c? Equal. So what must be true about alpha? So what would alpha have to equal? 1. And beta equals 1, either by symmetry or something similar. So the only possible is a plus b equals c. And now if you look at a special triangle, so what are our favorite right triangles? 45, 45, 90, and what's the other one? 30, 60, 90. The 30, 60, 90 comes from an equilateral triangle that you cut in half. These are the only ones we know. So if we believe in this, if this is 1, 1, 1, 1, then these all have to be 2. So the area of the square is 2 times 2 equals 4. And it's also 4 times 1/2 base times height, or 2. Contradiction. So there can't be a linear Pythagoras. Okay, so now. All right. I ran out of space, so I'm just going to copy the slide and just move it to the other. So if linear Pythagoras doesn't work, what should we try next? Quadratic. So alpha a squared plus gamma ab plus beta b squared equals, let's try c squared. Let's just try something like this. What must be true about alpha and beta? They have to be the same by symmetry, right? And then if you look at thin triangles, what must be true about alpha? 1. So only possible is a squared plus gamma ab plus b squared equals c squared. And so now we go back to our triangle. I'm not going to bother fixing this because we're running out of time. So if we do, this is 45, 45, 90. This is 1, 1, 1, 1, and this is c, right? So we would get the area of the square is c squared. Also, it's 4 times 1/2, and c squared is a squared, oops, which is 1, sorry. 1 squared plus gamma plus 1 squared. It's also 4 times 1/2 times base times height. So that's just equal to 2. What must be true about gamma? There you go. This is not a proof of Pythagoras, but it gives you a quick sense of, if you're going to try to prove it, what are the possibilities? And the only possibility is going to be a squared plus b squared equals c squared if you're going for something where all the terms are quadratic. You can argue there shouldn't be a c term because that's the wrong size. That's a length compared to areas. But maybe there is. Maybe there's a CA plus CB term. Law of cosine. Pythagoras is a special case of the law of cosines. You can prove law of cosines from Pythagoras. So again, the whole point of this is to show you that if you don't know what the answer is, you might be able to do some calculations and get a conjecture. I now have a conjecture of what to try to prove for Pythagoras. I'm not going to find a linear relationship that works, but I might be able to find a quadratic one. All right, this is a good place to stop. We will have one more Putnam review session on